traveled and dealt with the public, you will find the one thing that people, generally speaking, do not want to hear is the truth. Nobody is happy when they have to be faced with the truth.
Gravity has to be always attractive, whereas when it comes to the electrical force mediated by the photon, you can have both attraction and repulsion, as we according to general relativity, which is our basic theory of gravity.
Mm-hmm. General relativity is a very successful theory, I presume.
It has passed every test that we've thrown at it, and the tests, as the equipment gets more precise, the tests have become more precise. It has not failed in any test so far. Now, do you want me to go into what I consider a verification of prediction of string theory?
Yeah, I think that's important because up until now it's been basically mathematical extrapolations.
Yeah, but mathematical extrapolations that have to obey a plethora of consistency requirements and a whole list of things that have to be true of the theory that it's a mathematical test rather than an empirical test. But okay, let's talk about an empirical test. Okay, there was a very interesting experiment that was done on Long Island at the Brookhaven National Laboratory, where they were firing gold atoms at each other at very, very high energy to create what they called a quark gluon plasma. See, because I said earlier that protons are made up, and neutrons too, are made up of quarks and gluons, and that's what's inside the nucleus of a gold atom. The gold atom has 72 protons and a whole bunch more neutrons. And so if you bang these gold atoms together at high enough energy, the idea is it breaks them apart, and the idea is that the quarks and the gluons would come out very, very briefly for a fraction of a second, but they had a way of measuring what certain characteristics they would find. Now, what the particle physicists at Brookhaven were predicting was what they called a quark gluon plasma. What a plasma is, in that sense, is an ionized gas. Okay. In other words, a gas, something that functions as a gas, but it's made up of charged particles, so it's like an ionized gas. Well, before the results were in, some string theorists did a calculation to see what they thought would occur, and using a very, very exotic aspect, one of the most exotic aspects of string theory, which I won't go into detail because it's very complicated, but let me just say that using a very exotic aspect of string theory, they made a calculation that what the Brookhaven people would see was not an ionized plasma, but rather something more like a liquid that was extremely, extremely non-viscous, extremely much lower viscosity than water. Say water has low viscosity has to do with stickiness. Okay. and say water has very low viscosity, but say honey has high viscosity. Okay, so honey is sticky, water is not. Well, what they predicted was that what the Brookhaven people would see, rather than a quark-gluon plasma, would be a very, very non-viscous liquid, actually. And lo and behold, that is what they saw. They saw what the string theorists predicted, not what the particle physicists predicted.
So what is boredom? Well, contrary to popular belief, it's not when you have absolutely nothing to do. It's just when none of the options you have available to you appeal to you. Boredom is characterized by a lack of concentration, restlessness, but also feeling lethargic. It's really a state of being underwhelmed. But are we losing anything by avoiding boredom? Well, scientific research says yes. And what we're losing is important. When you're bored, your mind wanders. That's only natural. The state of boredom is one where your attention is not focused on anything in particular. Researchers have shown that this mind wandering is useful for creativity. They gave study participants a random boring task. The most boring one, reading the phone book. Then they asked participants to be creative, generate as many ideas as they could for what you could do with a plastic cup. Those in the most boring read the phone book condition generated the most creative solutions compared to less bored controls. A major
The other possible answer is we don't see them because of the way we see. That is, we look at the world around us and we see things by virtue of the electromagnetic force, light, travels into our eyes, allowing us to see the stuff in the world around us. According to string theory, it's possible that light itself may be trapped in our 3 dimensions, and it can't get off of our dimensions to move into the other one. Even if the other ones are big in this approach, we can't use the familiar forces of electricity, magnetism, even the nuclear forces to access the other dimension. It turns out that only the force of gravity will be able to move into these extra dimensions, and so it is our only hope of getting some direct evidence that the extra dimensions are there.
The fundamental nature of the universe and everything within is material, and all we see and know is nothing more than the emergent features of these tiny particles. But despite this, physicists are finding a different picture of reality. The old notions of materialism are fading away. Our universe doesn't appear to be material after all, but something emergent from a more fundamental underlying reality. Space-time and matter do not appear to be the foundation of reality, but an emergent construct of a deeper reality, and a new consensus in physics is emerging.